So in this video we're going to introduce the 5 Platonic solids just quickly. So the first one we're going to look at is the icosahedron, which is just here. Okay, so the icosahedron has got 20 triangular faces. Each face here is an equilateral triangle, and you can see there's 20 of them. If you want to count the faces, it's easiest if we just change the colours a bit. Okay, so here you can see we've kind of divided the icosahedron into a kind of blue cap on one end and a red cap on the top, and then a band around between the two caps, like so. And if we look at this, the blue cap, you see there's 5 triangles there, and the red one, you've also got 5 triangles there, so that's 10 altogether. And then if you look at the band around the middle, you can see there's 10 more triangles with alternating colours in this band around the middle. So that makes 20 altogether, 20 triangular faces. And then I'm going to say that there's 30 edges. So how can we check that? Well, it's kind of a little bit difficult if we just try and point to them one by one and count them. A better way to say it is to look at it like this. Okay, so here we had, as we said, there's 20 triangular faces, and so each of those triangular faces has got 3 edges. So that seems to give us 20 times 3, it's 60 edges. But if we do it that way, then we've kind of counted twice. You see, like this is really only one edge here, but we've counted it as being an edge of this triangle and also as an edge of this triangle. So we've counted it twice. We need to divide by 2. So because you had 20 faces times 3 edges is 60, but then we divide by 2, so really only 30 edges. Okay. That's what we see in this picture here. And then again, you want to count the vertices. So we could, one way to count the vertices is like this. We do the same sort of thing. We've got each of these 20 triangles has got 3 vertices, which makes 60 vertices altogether. But again, we're kind of overcounting that, right? I mean, if you look here, this is really only one vertex, but we're kind of counting it as a vertex of each of these 5 triangles here. So counting that 5 times. Similarly, this one here gets counted 5 times, once for each of the 5 triangles that meet at that vertex. So what we're supposed to do, we take the 60 vertices that we counted the first time, but then we have to divide by 5, because each there kind of in groups of 5 like this. So 60 over 5 is 12. There's really only 12 vertices here. Okay, so that's our icosahedron. And the next one we'll look at is the octahedron here. So the octahedron has got 8 triangular faces. Again here the faces are all equilateral triangles. We've kind of got 4 on the top like that and 4 on the bottom, so there's 8. And same sort of way we can count that there's 12 edges. We've got 8 triangular faces, which is with 3 edges each is 24, but that counts each edge twice, just as in the icosahedral case. So you have to divide by 2, there's actually only 12 edges. And similarly, you've got 8 triangular faces giving us 24, apparently 24 vertices, but you see that each vertex here is a vertex of 4 different triangles, so we have to divide by 4 to get the real number of vertices. It's 24 over 4, which is 6. Later on we'll be discussing the symmetries of all of these solids. So this one, the symmetry group is S4, a group of permutations of 4 things. That's our rotational symmetry group. So yeah. The way we're going to organise information about symmetry is in terms of the theory of finite groups and permutations. In this case, we get a symmetry group of order 24. Next, we're going to go to the tetrahedron. So tetrahedron is again got 4 faces, and again they're all equilateral triangles like this. And we find here, it's easy to see that you've got 6 edges. Here, just count them. There's, in fact, we can see all the edges here. There's these three like this that meet at this vertex in the middle, and then there's the 3 around the edge. So in this case we can just see all the 6 edges and all the 4 vertices, 1, 2, 3, 4. In this case, it turns out the rotational symmetry group here is the alternating permutation group A4, which has order 12, as opposed to the full symmetric group S4, which has order 24. Now we're going to look at the cube. Kind of simplest of these, really, in some sense. But now, the previous 3 cases we all had equilateral triangles as the faces. In this case, of course, the faces are all squares, and 6 of them. Yeah, there's 1 on top, 1 on the bottom, and 4 around the middle. 12 edges. So again, you can say there's 6 square faces with 4 edges each, makes 24, but then as usual each edge occurs twice from 2 different things, so we have to divide that 24 by 2 when there's 12 edges, or alternatively we can say there's kind of 4 edges around the top, 4 edges around the bottom, and then 4 vertical edges from the top to the bottom, and makes 12. Similarly, 4 vertices on the top, 4 vertices on the bottom, that's 8 vertices. In this case, the rotational symmetry group is again the permutation group S4 of order 24, exactly the same as for the octahedron, and later on we'll kind of see a good explanation of why the cube and the octahedron should have exactly the same symmetries. And finally, we'll look at the dodecahedron. Okay, so in this case we've got pentagons. We've got a kind of 5-fold rotational symmetry, and notice that that's kind of also the same as a 5-fold rotational symmetry that we see here. Okay, here there's if we look at it this way, it kind of looks like a pentagon. We've got 5 of these triangles meeting at every vertex. So there's a close relationship between the dodecahedron and the icosahedron, which we'll examine in more detail later. But here you can see there's 12 pentagonal faces. One way to think about that is you've got the top face there, and then the bottom face there, and then there's kind of 2 rings, right? There's the ring of these pentagons kind of in the top half, another ring of these pentagons in the bottom half, and if you think about it, you see there's 5 of these pentagons in that top half there, and another 5 in the bottom half, so we end up with 2 rings of 5, and one on the top, one on the bottom, makes 12 pentagonal faces. And we get 30 edges and 20 vertices. And in this case, it turns out that in a rather interesting way, it turns out that the rotational symmetry groups are alternating permutation group A5, the smallest non-abelian finite simple group of order 60. So that's the end of this kind of brief introduction to the five different Platonic solids, and there'll be some separate videos which examine more specific features of these, and will prove those facts that we stated about the symmetry groups.